Hello and welcome to this scientific discussion with now retired academic teacher and physics enthusiast Dr. Rob Johnston. Rob's PhD is in biochemistry, however he has taught physics at Dingwall Academy for 25 years and has been developing on a different aspect of physics than any other. He concludes that the standard expressions are inadequate and MKS system is preferred. I think we'll pass it over to Rob and welcome Rob.
Right. Well, this started with a desire on my part to express physical laws all in terms of mass, length and time, rather than coulombs and whatever you normally use, because they're not defined in terms of mass, length and time. So I rejected the CGS system, which is centimetre gram second, because of the nature of the units. I reckon that m to the power a half, L to the 3 upon 2, t to the minus 1 was not a good unit in physics, because it has something else in it, not just a charge. That's the charge expression for CGS charge, mass to the power a half, length to the 3 upon 2, and time to the minus 1. So I thought that's not good enough. So I went to the MKS system and I found the expression there, e squared over 4 pi epsilon naught r squared, and I thought that might be more adequate. Then I discovered that if I assume that epsilon naught, that is the constant in the MKS system, has the units of mass per unit length, I got a much simpler expression for charge. In other words, what happened was I found that the charge became mLt to the minus 1, in other words, linear momentum. And I thought that's much more likely.
And this is an alternative explanation.
It's an alternative explanation.
To the laws of force, essentially, isn't it?
Yes, that's right.
Okay.
So I went along that line and put E equal to mLt to the minus 1. When I did that, I found a whole lot of other things happen. You can write an expression for like h over mc, where h is Planck's constant, and the expressions like that become much more simple. Instead of having h over, if h over e is normally considered to be magnetic flux, which again has no defined units, in terms of mass, length and time. But if you let the E equal linear momentum, it becomes a length. So h upon e is a length, and h over 2 pi e, which is a very important length, becomes a radius of some kind of particle. So having done that, you can do that to the whole of physics, in fact, and you find that all the expressions are simplified, and you can get length expressions out of any quantity containing E. So that's very important.
So this has pretty drastic consequences.
Well, I suppose it is.
So potentially put the whole framework on its head, so to speak.
Well, it gives you mass, length and time expressions for things that are not expected to be mass, length or time.
Okay.
And in fact, there's a quantity which is h upon EC, where each c is the speed of light and E is the electronic charge. That becomes a time quantum.
Okay.
In fact, equal to 1.3795192 times 10 to the minus 23 seconds. So that's a very important point, because you can't write a time quantum containing the CGS units.
Mm-hmm.
It just doesn't work. There isn't one.
So the Coulomb system has been on the go for years now, and that's been the accepted norm
Well,
for charge.
there's nothing wrong with it.
So,
It just doesn't say very much. A coulomb means nothing. It's just a name.
yeah. Okay.
But a coulomb becomes a linear momentum unit, kilogram meter second to the -1.
Yeah, that's quite
I
extraordinary.
think that's very important. Also, epsilon naught is mass per unit length, which is what's called a linear density. So you can write expressions containing epsilon naught c. For example, the square root of epsilon naught h over c is a mass.
Mm-hmm. Mm-hmm.
It comes to about something times 10 to the -26 kilograms. And you find things like that, because that's very important, because it comes into the line as something similar to the mass of a proton, which is 1.672614 times 10 to the -27 kilograms.
Okay.
That's an example.
That's an example of your own work. Your
No, that's an example of standard work.
Okay. Okay.
That is a mass of a proton, 1.67 times 10 to the -27 kilograms is the mass of a proton.
Mm-hmm.
But if you have the square root of epsilon naught h over c, you find that that's very close to the mass of a proton. And the electronic charge divided by the speed of light
Mm-hmm.
then becomes 5.3442 times 10 to the -28 kilograms, which if you take 3 of them, they'll add up to a proton, roughly. Not exactly, but you don't expect to get it right first time and this sort of thing. But it's very important to realize that these particles which are got charge can now be translated into particles with mass. If you take, for example, I've got an idea that the mass of a quark must be somewhere around the mass of a proton, obviously.
Mm-hmm.
And there are 3 of them, so if you've got 3 these particles which have the radius h over 2 pi e, they have a radius equal to 1.316 times 10 to the it's 2 of these particles. The diameter of a quark
Mm-hmm.
is 1.316 times 10 to the -15 meters on that basis.
Okay.
But the radius of a proton is 1.32144 times 10 to the -15 meters, which is almost exactly twice the diameter of a quark. So if you've got that, you can just imagine that there must be some reason for that. That can't be chance.
No.
That's not chance,
Yeah.
is it?
Right.
I
It's
don't
amazing
think
stuff,
it is.
Rob.
Yeah?
Amazing stuff.
You what?
I think it's amazing what you've
Well,
discovered.
that's if you've got 3 of them in the nucleus, then it looks like the quark model, which has got 3 quarks in a proton. There are details, obviously, which are different, but the diameter of one of these particles is almost exactly the same as the radius of a proton.
Mm-hmm.
So that's not coincidence. That's because of some correctness in the basic physics involved.
Okay.
I'm not saying it's perfect, but 1.316 times 10 to the -15
Mm-hmm.
and 1.32 times 10 to the -15, the difference is very slight. So there must be a reason for it.
Yeah.
And the mass fits as well. Not quite, but that you would expect other particles to be involved in holding the thing together, so that's not surprising at all.
what do you refer to them as? Stick-ons or glue-ons or something like that?
That would be gluons. Yeah.
Okay.
I don't know what a mass of a gluon is supposed to be, and I don't think anybody else does either.
Okay.
Because they haven't got any masses to go on. I've got masses to go on, and I've got diameters and things to go on.
Right.
So it looks very much like that's correct. The basic correctness of the theory is manifest, if you ask me. But then I'm expected to believe in my own theory myself, of course. But
So I am joined here by another former student. I am a former student of Rob's. Rob has helped me get into university, and joined by Gavin Berkenheger, who is a former student as well. Do you have anything to add to the conversation?
It's all pretty deep for me.
Yeah.
I'm just trying to picture it all, like on the bigger scale, what it all means.
well, I don't know what it all means, to tell you the honest truth. I don't think anybody else does either. But there's something else I haven't mentioned, is the time quantum.
Okay.
1.3795 times 10 to the minus 23 seconds, right?
Right.
There is a constant which is very close to that, which is called Boltzmann's constant.
Yeah.
1.380662 times 10 to the minus 23, not seconds, joule per Kelvin. But I think it's seconds. I think that Boltzmann's constant is the same constant that I've discovered, H over EC. I think that's Boltzmann's constant, because there's another reason for thinking that. It's a time quantum, and K is Boltzmann's constant, is part of the expression for something called entropy. You know what entropy is actually the arrow of time, according to Eddington. And there's a formula for entropy and statistical entropy from Boltzmann's theory. And K, entropy S equals K log W, where W is a very large number from statistical physics.
Okay.
K, Boltzmann's constant. So if you can write an expression containing K for the arrow of time, as it's called by Eddington, I've got an expression for time which is just K, or H over EC. It's a time quantum. So the time quantum is very important in physics.
Yeah, well, I was looking last night and saw that I was trying to establish, we were discussing the other day, whether time is it the fourth dimension?
Well, it is at the fourth dimension.
Einstein didn't take it as the fourth dimension, I understand.
I don't know. I think it is.
But I think it's physicists now are sort of beginning to accept that time is the fourth dimension. Right?
Yes. Yeah.
We had a whiteboard of some of your notes, Rob. Is there anything that we'd like to develop on some of that?
Well, that's only basic stuff about the
is there anything else
units.
You'd like to
That's
mention?
just to determine the units of the system.
Okay.
Oops, sorry.
That's right.
That's all. That's the only thing that relates to what I'm talking about just now, is the time quantum may be defined as H over EC.
Okay.
The rest of it is just to try to justify my use of ml to the minus 1 for entropy, for epsilon naught.
Yeah, epsilon naught. Yeah.
And that's about all. And but no, I think that's all.
Yes. So what we're going to do, we're probably going to put this up on the video, so that we can illustrate that to the viewers, probably about now, so that they can see some of these notes. I think, is there anything else that you'd like to conclude with this introduction, Dr. Johnston?
Well, just the fact that the basic mass, length and time units that I have established are reasonable. I think that's basically important, because apart from anything else, even the relational closeness of H over EC to Boltzmann's constant is a very important point, especially considering that K is related to statistical physics in being related to entropy. And H over EC is a quantum of time.
Yeah.
So it's very close to Boltzmann's constant. I think that's a very important point.
Yeah.
But the whole thing needs to be discussed.
Yeah.
It needs people to know about it.
Yeah, that's the whole point of making this video, is
That's right.
to appeal to a wider audience
Yeah,
who may be able
that's
to
right.
contribute.
Because your sort of attitude of general physicists is it's all been done and dusted and that's it. There's nothing to be changed, nothing to learn.
So you're saying that these units, these are these units that you've come up with, it's easier to work.
I'm not saying they're easier to work with, I'm just saying that they illustrate something else.
All right.
That there is.
I mean, could you reconstruct our discoveries in physics using those?
Well, you
new
can
units, do you
you
think?
can use the same. You can get formula. You can find relationships that you wouldn't expect to exist. Like, for example, E, the charge. Nobody's bothered to think what that actually is. I find that it's a linear momentum along the fourth dimension. That's what I believe. And E upon C is a mass, and they're very close to nuclear dimensions and masses. 5.344285045 times 10 to the minus 28 kilograms, for example, is a mass, obviously. And sorry.
No, it's fine. No, I think do you have any more examples of that you'd like to mention, or would you rather let that?
No, but I understand that the units that we've been using up until now have obviously worked.
Well, they work if you want to stay where you are.
Yes.
Yeah.
But there are other reasons for wanting to wonder why, for example, E upon C is a very close particle to a quark.
Yeah.
That's a good point.
Well, you can see it all through nature. You see all these relationships that can't be explained.
That's right.
You see them. Oh, it's just a coincidence that is like that, or that's connected to that, and it's like, well, no, it's showing, like, you can see that there's some connection there. You can see there's some structure, there's some shape, or there's something there.
Yes.
But you can't put your finger on it because it doesn't fit with our standard model that we've got.
That's right.
So
Exactly. Yes.
yeah, maybe you're right.
Yeah.
We regress right back to the beginning and start afresh with different units and find new, if those relationships can be brought to life.
Yes.
Essentially.
That's right. That's exactly right.
Yeah. Well,
All right. I think we conclude with that.
That'll do for an introduction, won't it?
And this will be a part of a series of videos, potential videos.
Right.
And based on what the viewers may say,
but
we
obviously
can.
they want to see some evidence as well for this, rather than, because right now it's just talk. We don't have any.
That's right. That's something we can do in the next series of.
Well,
videos.
numerical so-called coincidences are one thing, but there has to be a reason for it. So it needs research to find out what these reasons are. It's not just a chance. It doesn't happen by chance that you get something looking like a quark coming from the properties of an electron or a proton or whatever it happens to be, a particle. You know, the sort of thing I'm getting at is it needs research, it needs work.
Yeah.
It's not just sufficient to assume, to believe in coulombs and not worry about what a coulomb really is.
Yeah.
That's not satisfactory physics. It's based on, well, it's not based on anything, it's just...
But you understand why the scientific community would just, stay away from, you're trying to destroy.
Yes.
Conventions.
Yeah.
But I suppose that's the whole
But
nature of
there's
science.
There's also the fear as well. If you're coming up with something totally new and radical, there's a fear there that people don't want to even go down. That's probably why
Mm.
people haven't picked up on it,
Yeah, well, that's true.
because you know,
No, I think we could leave it at that and see what happens in future,
Yeah.
and see where this takes us. Dr. Johnston,
Okay.
thank you very much.
Thank you.
Thank you.
thanks.
Thanks.